Hi, I'm Abe. I'm a data engineer at Etsy, and today we're going to be talking about Skyline, of which I was the primary author. And so we're going to talk about how we monitor, why we decided to build this, and how it advances the art of monitoring. So we'll get started. So Etsy is the world's largest handmade and vintage marketplace. We are based right here in Dumbo, so this wasn't too much of a pain to get up here. And we have a large stack. We've got a lot of stuff going on. Specifically, or actually not specifically at all, but these are just some of our numbers of some of the servers that we're dealing with. 41 shards of MySQL, 24 API servers, 72 web servers, 42 Gearman boxes, a 150 node Hadoop cluster, 15 Memcache boxes, and around 60 search machines, and a lot more than that, probably on the scale of 100 to 200 for other various services, kind of one-off things that we have. And that's not to mention the app itself, which is running on top of all these machines and all the services that are actually running on these machines. In addition to that, we practice something called continuous deployment, which is kind of the new hotness with DevOps, right? It's kind of always deploying every single day. So we deploy around 30 to 60 times a day, every day, and we make this really, really easy to do for all our engineers. Deploying, of course, means a lot of different things to a lot of different people. In our case, and in probably everyone's case, it means taking new code and then putting it on your web servers to be serviced. And this can get tricky because people are always visiting your site all the time. And like in Etsy's case, we're always making money every second of the day. And sometimes we're making more money than other times, but we're always making money. And so if we want to make our services better, we have to figure out a way to deploy without taking the site down. And so we have this whole continuous deployment infrastructure to let us do that efficiently and quickly, so that when someone has an idea to make their feature that they own better, they can that day push a button and deploy it. And the whole process takes about 10 minutes. So we're very, very proud of that. Of course, with this process, the whole point is democratizing deploys, right? It's not like you take your code changes and then go give it to the high priest of deployment somewhere deep in the bowels of the ops department. No, everyone deploys. At Etsy, we have about 250 committers, and not all of those guys are engineers, right? We have PMs who deploy, designers who deploy. In fact, it's so easy to deploy that on your first day, you're expected to deploy new code to the web stack by putting your face on the About page. And the way you do that is with the big green button, and you literally just press deploy, and then it does it. And it's terrifying. And so you're probably thinking, like, we've got hundreds of these boxes, right, these servers, and they're hosting constantly evolving code that's changing up to 60 times a day. It must be a miracle. Like, how do we even stay up at any time, right? How do we not just burst into a pile of flames, given that the fact that there's so many haphazard ways for things to go wrong? Well, we optimize not for avoiding failure, we optimize for recovering from failure. And the concept this is called mean time to failure and mean time to recovery. And it lies on a spectrum, right? If you optimize for mean time to failure, that means you want to never fail again. That means your mean time to recovery is very, very long, right? So for example, we really, really heavily protect our credit card stuff. That's what all PCI compliance is for. Because the mean time to failure there, the mean time to recovery is really, really long and painful. And so it's much less painful to just optimize for increasing the time to failure than reducing the recovery time. Because once you lose credit card information, you're in a lot of trouble. However, if you're dealing with stuff in the web stack that is easier to fix, like if a process dies, you just bring it back up. If there's a bug in your code, you redeploy 5 minutes later and you fix it. And this is optimizing for mean time to recovery. So we anticipate failure. We anticipate things are going to go wrong. We anticipate boxes are going to have hard drive failures, and that humans, developers, are not infallible, and that they will introduce bugs in the code, despite their best efforts. But we don't penalize them for that. We kind of look at it from a systematic view, and we try to just make it as fast as possible to recover once we have detected a failure. And that last part's very crucial, detecting a failure. How do you detect failures? How do you know when something's going wrong? When you have all these different people doing all these different things on all these different services and servers. And so to that effect, you have to realize that you can't fix what you don't measure. So we have taken a pretty hard line stance on just measuring every single thing in our infrastructure. And to do that, we've got a bunch of tools that some of them you may be familiar with and some of them you won't be. So on the not homemade side, we use Ganglia for our more deep operational level metrics, Graphite as a time series database to store our time series, Nagios for alerting. We use StatsD, which you probably know about, which is an aggregating daemon, right? So we'll go into it in a bit. SuperGrep, which I'll explain, and then Skyline Oculus, which is what this talks about. So we'll start with the most basic defense, SuperGrep. So SuperGrep is a really, really, really simple tool that it allows us to detect errors when they occur. And all it is a node app that's tailing log files. Literally, it's tail f access.log for your Apache access logs and everything else logs that you want. Pipe grep -v minus the things you already know are going to happen, error. Like you're searching for error or failure, whatever indications of failure that there are in the logs. And then you just load this up in your web page, and then this just goes streaming by. And then when there's an error there, since the whole site is being trafficked very heavily, like the entire page will just flood red with the error, and you'll know something's wrong. And so the Etsy parlance for that is SuperGrep angry, or SuperGrep blowing up. And so this is a really, really simple way to know if there are errors being thrown, right? Because when there are errors being thrown, you can go fix them. And that's how we do it. So after you push, you kind of go hang out with SuperGrep, and you look to see if everything looks good. And then you have more confidence that your push didn't break everything. But that's not really enough, because there are certainly many ways for a service to break and to be not functioning and to be failed without it throwing a specific error telling you that it's failed. There are a lot more subtle ways for things to go wrong. And so for those, one of the ways we handle that is through StatsD. So what we do with StatsD, and this is the mythical monitoring dust that I referred to in the abstract for the talk, is it's also pretty simple. It's a 300-line node file, and it sits there and it listens for pings to it. And these pings look like this in your code. So you're sitting there and you do something in your logic, and then when you do that thing again, you can call statsd.increment whatever your metric is with the namespace in there. And we have a bunch of different ways there's increments, there's gauges, there's counters, like there's a bunch of different kind of ontologies for StatsD metrics, but they all basically do the same thing. And the purpose is to graph metrics that otherwise would not be graphed by SuperGrep or by Ganglia, right? So these are lots of application level stuff, but not necessarily. Like you can throw it anywhere there's code running. You could throw a StatsD call, and then it'll get aggregated by the StatsD daemon waiting on one box, and then it'll get sent and flushed to Graphite. And so with one line of code, you've got an entire historical Graphite series from that point forward, right? And then once it's in Graphite, you don't have to, roll-ups are taken care of, aggregation is taken care of, you get all these Graphite functions, you can have a graph of the data, you can take it out and have JSON and do all this great stuff. And so all that comes from just a StatsD integration. And so like I said before, this logic comes from this philosophy of if it moves, graph it. Right? If anything is moving in our infrastructure, you want to graph it. Even if you don't think it's important, even if you don't think it's a business level metric that could possibly ever impact failure, you want to graph it because you don't know what's going to happen. And even if it doesn't move, you still want to graph it. Like put a StatsD call in there because it's so easy. There's no friction to do it, and that's by design. There's zero friction. And so this way we have just metrics infiltrating everywhere in our stack. And so once you have those metrics, you put them into dashboards. We do have an open source dashboard framework. It's nothing special. It's just it's a wrapper around Graphite. And what we do with that is each team has the ability to make their own dashboards where they kind of cherry pick the most important metrics that they think are relevant to them and put them in dashboards for easy access. And so that was the flow before Skyline. And of course, when you just have dashboards, the problem with dashboards is that when you have an avalanche of metrics like we have, when you have, and the specific number is 250,000 StatsD calls and Ganglia and a couple other metric namespaces, that's a 250,000 total, which is an absurd amount. It's way too much for dashboards, right? And we've got 250 committers. If we were to have every committer looking at graphs all day long, that's a dashboard to engineer ratio of 1 to 1,000, right? You'd have to have all your engineers looking at 1,000 graphs every day just to monitor everything that you have metrics for. And so dashboards don't really quite cut it at that scale. And so what you end up with is a situation where things could be going wrong and no one's seeing it because A, there's no dashboard for it. B, if there is a dashboard, no one's looking at the dashboard. And so if no one's looking at the dashboard or otherwise not aware of this metric that's spiking or doing something that's not supposed to be doing, no one can act on it and either decide it's a failure and fix it or decide it's normal and not fix it and but be aware that that is what it looks like. And so to kind of counteract this, we do use Nagios. We're very heavy users of Nagios, or Nachos, if that's how you pronounce it. Nagios sucks, and everyone likes to say how much Nagios sucks. There's a lot of friction to develop a Nagios plugin. You don't necessarily always have confidence that your Nagios plugin works, right? Because you can write the plugin and then it'll pass green because you think it's right. But that doesn't to test that as wrong, you have to take your service down, which you can't do. So now you've got like a dud metric that you think is working, right? And that's dangerous. Nagios is stupid. There are thresholds that you manually set, and it's say you've got a disk space slowly filling up on one box, right? And then you have a threshold, like 85%, alert me when this is happening, so I can clean the box up. And then Nagios decides to wake you up at 3 in the morning because look, the disk space is at 85% now, but that's been slowly climbing for 3 years. Like it did not have to wake you up at that particular moment. So it doesn't know. It really doesn't know what normal is and how it should structure its alerts. And you can't just tell it to. That's really hard. So Skyline was meant to kind of take this the next step forward. And of course, there obviously aren't Nagios alerts for everything, right? Because we have this whole wealth of metrics. And there isn't 100% metric coverage for Nagios. There is an argument that says, maybe you don't need 100% metric coverage. Like it's really only good to monitor things that are like mean things. But Skyline, the design of Skyline is to take the long tail of everything, right? To just say everything could be valid, err on the side of noise, and give you the metrics that are spiking. And that's all it does. And then it's up to you as the engineer to act on those if you choose to. All right. And so Kale is the thing that we came up with to do this, and it's composed of both Skyline and Oculus. Skyline is the anomaly detection part of things, and Oculus is the metrics correlation part of things. We're not going to talk about Oculus today, but the way it works is you can find a metric, and you can see what other metrics at that time look similar to it, right? By like literally how the graph looks. With the logic being, if something's messing up, probably it's not messing up in isolation, and probably there are other things that are also messing up that would help you get a broader picture of the problem and diagnose it and then fix it. So but before you can do that, you have to know that you have something wrong in the first place. And so that's what Skyline comes in for. So we have a question. The question becomes, how do you analyze a time series for anomalies in real time, given this structure pre-Skyline? And it's actually pretty easy. You can just make a lot of HTTP requests to Graphite's API. Right? Graphite's got a really, really awesome API that you can hit and get perfectly structured JSON data back, and you can take your JSON and you can run algorithms on it, and you can just keep hitting it once every 10 seconds or so for as many metrics as you want. And that's a way to do it. That was what the prototype of Skyline was. But that doesn't work when you hit our scale. We need 250,000 metrics because Graphite's going to disk to retrieve historical data, and it can't handle you hitting 250,000 requests for all these time series every 10 seconds if that's the resolution you want. It's not going to happen. So you need a dedicated service, and so that's where Skyline comes in. So to reiterate, Skyline is a real-time anomaly detection system. Let's dig into that. So real-time means a lot of different things in a lot of different contexts, and in this context, I'm kind of lying. It's real-time enough on 2 levels. So the first level is that we do a stats data resolution of 10 seconds. So that means every 10 seconds, no matter how many stats-D metrics you've received, it flushes to Graphite every 10 seconds. So you're not going to get higher resolution stats-D data unless you specifically set 1 second. But the convention at Etsy is to stick with 10 seconds. And Ganglia, we use 1 minute resolution. Right? So you're not going to get more than 1 minute resolution. You can tweak this, but we don't do it. And so that's what we're dealing with. So the best case scenario, even if you could analyze, process, and store instantly, is going to be 10 seconds for the stats-D ones and 1 minute for the Ganglia ones. Of course, you're not doing just that. You're also processing them, right? You're just going to store them somehow and then take them out and then process them, run your algorithms. And so right now it takes about 70 seconds with our throughput, right? So that's not so bad, right? It's really not bad. And it's even better when you think about that it's still faster than you would have discovered it otherwise, right? And that's really where this shines. As long as this is faster than you would have discovered it otherwise, which is in most cases never, this is good enough. And so at this point we could optimize it, right? But it's an improvement. So onto the architecture. When you're talking about making all these requests and kind of playing with data at the speed that we would like, memory is a much better storage medium than going to disk, which is why Graphite wouldn't work in the first place, because it stores its metrics as Whisper files, which is a round-robin database on disk itself. And we don't want to have to go to disk to get a certain time series that we want. We want it to be already in memory, easily accessible. So we chose Redis to do this. Redis has a great API. It's rock solid, at least for what we're doing with it. We don't use the Redis cluster yet, which I don't think is mature at this point. But it's got a lot of cool data structures, really great community, and it's a really solid tool. So we were excited to use it. And the question then becomes, how do you get a 250,000 time series into Redis on time? And the answer is to stream it, right? If you can find a stream. And so we looked around for our stack for a stream of metrics, if we could get them, because we didn't want to have to like how are you going to get all these kind of varied Ganglia metrics and stats-D metrics all in this one place? We didn't know what to do. But then we looked at Graphite, and we realized like they are already going to one place. They're going to Graphite, and that's cool. And in addition to that, we also use this thing called Graphite Relay. It's called Carbon Relay, and what it's built for is a redundancy thing, right? So you have your stats-D and your Ganglia. Your stats-D is already one aggregation, then it's sending everything to Graphite, and Ganglia is sending everything too. And then Graphite will take all that stuff and store it on the listener. And if you do it that way, that's cool. But then if that box goes down, which you have to assume it will one day, then you've just lost all your metrics and you're blind until you can get them back up. So what we do is we have a relay listener. So our streams, our stats-D and our Ganglia ping to the relay, and then the relay will immediately, upon receiving the metrics, send them over TCP to a backup Graphite and to the local Graphite listening on the same box. So now you've got like you're making TEAD writes essentially to two Graphites, and so that way you can have redundancy. And then the way it does this is it sends pickles over the wire to the other backup Graphite, and so that way if one box goes down, it's no problem. You have another one, and you can just bring it back up and keep going, keep deploying, and keep operating. And so we saw this and we were like, okay, we can just trick Graphite and say, instead of relaying to a backup Graphite, we can just relay to Skyline, right? Skyline's perfectly capable of listening on a port, which is what Graphite does, and consuming data, which is exactly what Graphite does. So we just emulated the Graphite protocol. We have a pickled listener. It's written in Python, so it's easy to do pickles. And then we just have a listener, and the original Graphite doesn't know that there isn't another Graphite listening, right? But so what it's doing is it's sending to three things now. The relay is sending to three things. It's sending to the original Carbon cache listener on localhost. It's sending to the original redundant Graphite on that box, and it's also sending it to Skyline, right? So we've got three separate streams. But the upside is that Skyline now has this awesome stream of data, and that includes Ganglia. And Ganglia is also an awesome thing because out of the box, it can write to RRD files. So we've got a script that will go in and import it from those RRD files. Cool. So we have our stream, and it's going to our box. So we've solved the hard part, maybe. Now what do we do with the data? Right? We have to keep it somewhere. Unless we're going to talk about doing strictly online stream processing, which we're not going to talk about, we have to store them somewhere to then take them out and analyze of the duration. So when you want to think about doing this, we're keeping it in memory, right? We're keeping them in Redis. And you have to have two things in mind when you want to do this. You want to minimize both I/O and your memory footprint. And those are for both fairly obvious reasons, right? Because I/O, you're both putting things in, consuming them, and taking them out, right, for the analysis stage. And Redis can only handle so much. Even though it's really, really good, it can only handle so much. Similar with the memory, you have to, there's a limited amount of memory. You can store a limited amount of metrics for a limited amount of duration. And you want to get that as small as possible so you can pack it the most as possible within your confines. So to do this, we chose to store the data as strings in Redis. And that might seem counterintuitive. Like Redis has a lot of cool structures that might seem better for storing time series, like lists for one. But the problem with lists is that you take them out and it's log n time to take them out, which is not ideal. Whereas with strings, it's constant appends and constant withdrawals, right? Which is awesome, right? And actually, that's kind of a lie. Strings, as they get longer and longer, Redis does not handle them well, but it's still like orders of magnitude better than any other data structure in Redis. So we have to deal with it. And then we use the append. So normally you would do a get and a set. With append, it's just it's an atomic set, and it's guaranteed to be in order. So it's super, super awesome. And so we save ourselves. We cut our gets in half, right? We only get things when we want to analyze them, and we only set them when we want to update the time series. So we have our strings in Redis, and now we have to think about how we're going to structure it, because you can't just store data in the form of strings in your storage. So you might think that JSON is the answer, and we did think that for a while. It's fairly straightforward. It's easily appendable, right? So say a data point came in, and this is our series. Another data point comes in, you just append it on top, and then another data point comes in, you append it, and then you have almost valid JSON here. When you want to take it out, you just withdraw that metric, append brackets on either end, and then it's valid JSON that can then be decoded in whatever language you're dealing with. And this seemed all right, but we found that over half our CPU time was spent decoding JSON, which is, in my opinion, a silly, silly problem to have. We wanted to save CPU cycles for the hard things, like analyzing the actual time series, right? Things that are harder to be optimized. JSON decoding is just a kind of very low problem that we're above that, right? And we can kind of look into why that is. So here's a bit of JSON data. It's an array with two things in it. If we break it down, we're realizing that the things we care about are in the minority, right? We only care about the 1 and the 2. We don't care about the comma or the bracket. But the reason that stuff's there is because the CPU needs it to decode the JSON and turn it into an actual object in your language. And the way it does this is it does a scan. Like it looks at, okay, this is a bracket. This is a 1. This is a comma, so it's a new element. This is now a 2. Okay, I still don't know what's going on. Oh, it's the closing bracket. Okay, is there anything else? No. Okay, good. I have an array. Bam. But what it's done there is it's scanned the entire string, right? And there's no metadata to tell it to skip this thing because it's stupid or pre-allocate memory because it doesn't know. And that's a waste of CPU cycles. So we looked around for things that do have metadata in them. And we found MessagePack, which is really, really awesome. And what it is a binary-based serialization protocol. It's in the same class of things as protobufs and Avro and Thrift, which are all, they're meant for RPC, right, communication. They're not really meant for storage, but they do solve the problem that we needed, which was speed of decoding and size, right? Because you want to send things over the wire, you want it to be as small as possible, and you want it to be easily understood at both ends. So this actually solved our problem. And so we can look at what MessagePack looks like. It has metadata, and the metadata consists of headers. Okay, so the header here is that we care about is the size of the array, which is going to be either 62 or 30-bit big Indian integer that basically tells the CPU, okay, this is how big my array is, and you have to obey that, obviously. But you just append your two things on there, and then that's a concise thing. And so now the things that we care about are in the majority of the actual data we're storing. We're storing a minimal of metadata, And MessagePack is also supports appending things, right? So you can just append it on. You've got MessagePack now, and you can just unpack that, right? And that's really super cool. And so the result of doing this, of switching over from MessagePack to JSON, is we cut our CPU time in half. And it's still a big problem for us. Until something better comes along, we're stuck with this. But it's significantly better. And so I would recommend in just about every situation where you think of using JSON to use MessagePack instead, unless you're dealing with the browser. So anything internally, there's no reason to use JSON, and it's really a drop-in replacement. And the APIs that people have wrote about MessagePack, they wrote it with that in mind, to just replace your JSON with it. And so, okay, so now we've got things coming in, and they're being stored to time series on Redis, and they're being appended. And if we let it do that forever, we're going to run out of memory, because we keep appending and appending. We're not getting, because we didn't want to do that, right? Because that's more I/O. We're appending, and it's going to run out of memory. So we have a process called the Roomba that goes through occasionally, and it will clean the data, and it will make a get, but it runs less often, and so it's kind of negligible. And it'll run through, it'll get everything, it'll trim off the excess duration, and then it'll put it back in, right? And so in this way, we store a continual rolling duration of 24 hours for each metric. And unfortunately, we can't go above that, because then performance really starts to suffer. So yeah, we wrote this in Python. As I mentioned before, it might seem like not a good idea to write a heavily concurrent architecture in Python, but we chose it because it has really, really good math options, like NumPy, SciPy, stats models, pandas. Like these are really lively areas, and they're pretty good. And so even though it's not that great for parallelism and concurrency, we had more faith in our skills as engineers than statisticians. So we opted to slog through the engineering in favor of an easier time handling the math bits. So that was why we chose that. And then the rest of the architecture is pretty simple. That's the entire consumption architecture. And on the other side, we have an analyzer. It's based on a very simple map-reduce design. It basically, it just takes, I think, 30 processes. However many cores you have is how many processes you should have. And then it will, at the beginning of each run, assign all the keys in Redis to a process. And then that process is responsible for decoding that slice of keys and analyzing them and everything. And then at the end of the run, all the results get compiled into one JSON blob that the front end will go and get every couple seconds, right? So in this way, it's refreshing. And you're seeing a constantly updated view of what is anomalous. And so here's what that front end looks like. We'll do a demo later, but just so you get a taste of what we're talking about here. All the metric names are there. So you kind of go through them, scroll through them. The actual data point that triggered detection is there as well. So that's how you know, and that's what the red line is, so you can kind of visualize what the computer's thinking a little bit easier. And then you get two views of your metric. The first view is the last hour, and the second view is the last day. And that's just for more context, because oftentimes what looks anomalous with an hour does not look anomalous when you consider the broader context, and vice versa. So you get both views. And again, we only store about 24 hours, or exactly 24 hours. Cool. Okay. So I've talked about anomalies without defining what it means to be anomalous. So the way we handle the actual analysis part is through a consensus model. So the way that works is it's a vote, basically. We have a bunch of algorithms implemented, and then each time series is run through all those, and then they either return true or false. This is anomalous, this is not anomalous. And what you get is if the majority of them, you can set this parameter, like if 6 say yes, it's okay, or 7 if you want to be stricter. We'll vote that it's anomalous, then we consider it an anomaly, and then we surface it to you. And the reason we do this is because it helps for mismatches within the model with respect to the time series, that the actual data, and what your algorithm is running on, right? You might one idea that was proposed was why don't we go the finance route, right, and just make it a strictly forecasting problem, and just you can do an ensemble of forecasts and then average them out, and then have that's your forecast. And if it's significantly different than that, then that can be your anomaly. But the problem with that is that it's opinionated. And we found that like we had so many different kinds of data, like that didn't really work in all cases, and it really limits you into what you can do. And so you can still do forecasts in this, but what you can't do is get a sense of how anomalous something is, because they're all different algorithms. How anomalous something is on one algorithm doesn't really relate to how anomalous it seems on the other. So that's one problem with doing it this way, but the upside is that you can implement anything that you get your hands on, as long as it returns true or false. So we thought that was a pretty significant upside. So that's why we opted to do this. And the basic idea is, behind the algorithms that we have implemented at this point, is as follows. So it's a metric is anomalous if its latest data point is over 3 standard deviations above its moving average. Right? So you've got your time series, right? You've got standard deviations from the time series, which is like, that's the normal variation, the normal noise. And then you've got 1 standard deviation up and down, 2 standard deviations. And then if your latest data point that comes in is like up here or down here, right? If the absolute value is over 3 standard deviations above or below its moving average, then you would be justified in saying that this is an anomaly and that I want to know about it. This is from statistical process control, which was invented in the 1920s, I think, by a guy named Will Shewhart. And it was made because this is when the assembly lines were coming along, right? And you had these huge operations chains, and you had to know like what parts are working. So you had what are called control charts, which are essentially exactly this. Like you have normal lines of variation, and then when your screw or whatever is outside, when the width of your hole that's being screwed is outside that line, then you know you have an anomaly and you should fix something. And so just to visualize this one more time, here's your regular bell curve, right? This is the normal distribution, and your mean's right there in the middle. So these are data, like values of data, and when your data point lies within that the 3 sigma there, then that's how you know you've got an anomaly in the best scenario. So to implement this, we kind of riff on this. We kind of achieve this in a bunch of different ways. First way we do it is by histogram binning. So you get your data. Here's a real-time series from Graphite that did get surfaced by Skyline a couple hours ago when I was making the slides. And you take your most recent data point, so that's 40 there if you can't really see. Is it a laser? Oh, so yeah, you got your data point there, and then follow that, and that's 40, okay? And then you make a histogram of the entire time series, right? So this kind of looks like the normal distribution, right? And you can see like when like histograms are distributions of the data, and so when there are smaller bars, that means less values are the value that you're calculating for. So if we look at 45 on here or 40 on here, we see the bar is really small, right? It's like really, and that's in the 3 sigma area of this distribution here. And so to just check, we just check which bin that data point is, the 40 is, and we see it's right there. And so that's a really small bin size, so that's an anomaly, right? That's one way to do it. Another way to do it is by linear regression, right? So take a best fit line via ordinary least squares, which is a very common linear regression algorithm. And then, so you have your data again, you fit a regression line on it, right? And there are problems with this, which I'll go into in a bit, but bear with me for now. So you fit your regression line, and then you take the residuals, which are the errors of the mean of your regression line, or just the line itself, because this is a data point too. And you then take all those and then find the distribution of those, right? And then you've got your 3 sigma here, which is your 3 standard deviations, and that would be the anomaly there, right? So that's another way to do it. A third way is through median absolute deviation, where you basically take the median of your time series, the middle value that occurs the most often, which is going to be in the highest bit in your histogram distribution, and then you calculate the residuals with respect to that. Okay, so you calculate how off every other value is with respect to that, and then you find the median of that, right? And if that is outside 3 sigma, or whatever test statistic you want to use, then it's an anomaly again. So these are all kind of different ways to do it. I think I have one more here. All right, so this is a broader technique that we want to use too. So instead of using averages, it's generally recommended to use exponentially weighted moving averages, and that's because data, like monitoring data and operational data kind of gets less valuable as it gets older. You know, like when we're capacity planning, we don't really care what our data, our page views per second performance time was in 2009, right? It's not really relevant. Our whole stack has changed, and so we can apply this to this problem as well. So instead of just taking the entire time series and using all the values and treating them equally, we can add a decay factor to the time series, and then so that way the more recent values are treated more with more importance, right? And so in that way we can know what's normal based on what's happening right now, and not really care about what's happening in the past. And so this discounts the older values a little bit to give you a little bit more accurate and to make it a little less noisy. So that's a technique. And you can apply the exponentially weighted technique basically anywhere. Like just weight things, right, according to where they are in your data. So that's one technique. But there are a lot of problems with this. So Skyline works, but there are lots of things it doesn't handle, and I want to go into them right now, so we can think about how we can solve these problems together. So these are the 4 horsemen of the model apocalypse. They are seasonality, spike influence, normality, and parameters. Okay, so first one's pretty straightforward. You might think that this is an anomaly, and if you saw that on Skyline, you'd be like, hey, thanks Skyline, thank you for showing me this awesome thing that doesn't look right at all. Until you look at the 24-hour view and realize that it is probably a cron job. It's highly seasonal. It should be happening. In fact, I want to know if it doesn't happen. How can I get Skyline to tell me this? How do I know? Your regression lines are going to totally fail here, right? Because the average of this, if you take a regression, it's going to be like right in the middle, right? And that is totally worthless. It's not going to tell you anything. And the deviations of that are also worthless, right? This distribution curve is not going to be a normal distribution. So our algorithms totally fall apart with seasonality, and that's one of the problems that we're working on. And the thing is, like, once you detect that something's seasonal, it's easier to build an algorithm, but these are very expensive. But we'll get into that. So spike influence. So when you have, say, you detect an anomaly, and you got your spike, and everything's working well. But then when you're using this whole 3 sigma paradigm, your moving average, even if it's exponentially weighted, is being artificially bumped up, right? So you have the same problem of having your average be much more than everything else just because it's like the tent effect, right? And so you'll miss another anomaly that comes, even if it had breached, like say the first anomaly didn't happen, it would have been detected if that anomaly hadn't happened, but since it did, the average is moved up, the threshold for 3 sigma is moved up, and you've now got an anomaly that's kind of slid by you. So that's a problem. And to fix that, you have to kind of like remove the outliers, right? Or kind of retroactively go back and change your data. We're reluctant to do those things because we're trying to detect outliers in the first place, right? And we don't necessarily want to change data. So that's another problem. The third problem is normal distributions. This is the real big one. So real world data doesn't really follow normal distributions, right? Like all these algorithms are kind of like, they're developed in what's equivalent to the data, like a pristine data environment, where everyone's got a normal Gaussian curve and life is dandy. But that's not true for lots of real world data. And the reason statistical process control was able to get away with it and was able to be so influential is because they're dealing with fundamentally different things than we're dealing with, right? They're dealing with car assembly lines and with screws that are supposed to be like defined widths, and they have specs, and they know exactly what they want. And it's very easy to, like, if you have a drill bit that drills holes all day long, you're going to have a really, really nice distribution curve because it's doing the same thing, and you know what it wants to be doing. But we don't have that, right? We don't have that luxury. There are no specs for our systems. We build them because we have to serve users. We don't spec it out. We have no idea what normal is really, as long as, like, besides you log on to Etsy.com and it serves you. Beyond that, like it's not apparent immediately like what a normal flow of data through the system looks like, because it's a complex thing, and there's different moving parts. And like this is the disk I/O weight on our database, right? It looks terrible, right? But our site's up, so is it normal? Is it not normal? I don't really know. I don't know. I don't have access to all the data. of all the components that are making that particular graph behave the way it's doing. So I don't know if this is actually a good thing or not. And as a result, I don't get the luxury of knowing what is normal and what is not normal. So to kind of reiterate, when you have simple systems, like just a drill bit and a piece of wood, you have very simple definitions of what anomalous is. But when you have complex systems, you have very complex definitions of anomalous. And that's not necessarily, you can't really reduce that to a simple matter of this metric is bumping. Like that doesn't translate to your system is failing, right? And that's something to watch out for. And of course, in addition to complex systems being complex, even if we were to nail it down at any given time, they're evolving, right? Because we're deploying all the time. Our systems are changing. We're bringing servers up, we're taking them down. We're changing the app code. We're getting hit with more traffic because Obama tweeted us. These are things that happen, and we have to be able to adapt to it. And our monitoring has to be able to adapt to it too, right? And so Skyline was built so that it can be adaptive. Like it's more adaptive than Nagios, which will just trigger over the threshold, but it's still not enough. And we're still trying to think about how to get it to be more adaptive. And one example of that is, all the time we take out shards to do rebalancing or something, and then Skyline will detect that, which is awesome, right? But it's a false positive. It's something that we know is happening. What's a good way to kind of shut that off, right? And now we're getting into the kind of the area of alert design, right, and user interface, which is not the focus of this talk, but it's another thing to think about. And the fourth horseman of the model apocalypse is parameters, our parameters. So to kind of back up on a broader, so this is a graph of we're doing capacity planning right now, so I had this graph handy, and this is our page views for since 2009 to right now in the blue. And so I modeled it. I wanted to make a nice prediction, and so I made a prediction in a model. And this is it's a nice model. It looks pretty good, right? Like that visually, it looks like that is what our demand is going to look like in terms of page views. And the problem is I spent a lot of time making this model and kind of custom fitting the model to data, making sure my assumptions were good, fitting my parameters, right? And what parameters in general, that's kind of a term that you might see get thrown about, like parametric versus non-parametric. In general, so when you say something's parametric, it's like not machine learning, right? Because machine learning, and I could be completely wrong about this because I don't do much machine learning, but machine learning is when you just say like machine figure out what the best model is, right? And figure out what parameters you need and what those values should be. Whereas with parametric models, you set the parameters, right? So these are like different gauges of your model that you set to fit it the right way. So the parameters for this model that I had was that it was seasonal, right? So I had to say like, okay, treat every data point on a 365-day season, right? So only compare it to the data points 365 days ago. Give a certain amount of weight to the overall trend, but also a certain amount of weight to the seasonal trend, right? Like these are different kind of impacts. Give it an exponentially weighted smoothing factor to kind of discount the older data and do all these things. And then once you have all that, once you've defined your parameters, you want to fit it. We do a bit of machine learning. This is like the most basic application of machine learning, where you train the data. So basically run it against all your different parameters until it finds the lowest root mean squared error, right? So until it fits the most, and then there's your model, right? And so those are two things that are really, really expensive to do. And they do not lend themselves very easily to being automatically done on a massive scale across 250,000 of these metrics. So that's a really big problem, because then you're dealing with models that don't even fit your data, and you're trying to detect anomalies with those models. And when it's not feasible to hand fit all your models to data, what do you do? This is a problem that we're dealing with. And so you can't have good anomalies without good models. And so as you might have guessed, a robust set of algorithms is the current focus of this project. We've got the architecture pretty much set. It's not distributed yet. It runs on one box, and we want to keep it that way, ideally. But yeah, so the hard part now, and this is going to take a while, but the hard part now is just figuring out how to solve these problems with our models and with our algorithms and with our data. So that's all.